in my presentation. This is the thing, right, which will go.
Yes. The light is
Laser. Moving slides. Okay, that's great. Okay, thanks. Let's start. Sorry for the delay in the technical thing. So I'm Raj Das. So I'm from MIT University, Australia. If there's a prize for coming from the farthest distance, I'll certainly get the prize in the conference. But anyway, with the time, I would like to tell you what we're telling. We have a large program on fatigue characterization of a series of additively manufactured materials, particularly focusing on our defense industry and aerospace industry. So what I'm going to present are part of the work where we are focusing on aluminum alloy, which is not many people focus on AIM, and aluminum alloys are very important for aerospace application. And we are going to show you the result for how we are finding ALSI, aluminum silicon alloy, for the properties and characterization for additive manufacturing. So that's the key focus of my talk. We want to understand the traditional thing, surface effect, subsurface effect, and porosity on laser powder bed fusion aluminum alloy. The authors, my co-authors in this presentation are Laboni Afroz, the PhD student who did most of the work and the experiments, and Mark Easton and Qian, our professors and colleagues within the Center for Additive Manufacturing and School of Engineering. So we don't need to go in details. We know there are a lot of benefits of additive manufacturing, particularly what we didn't notice so far. It has significant benefit for aerospace industry as well, because of the lightweight aluminum, which is favored by aerospace community. Now, if we can introduce aluminum alloy and overcome the issues, particularly at the end of the day, with certification issues, then we will be able to deploy complex parts, just-in-time production in aerospace. So this is what the focus of this talk. So for aerospace, the fatigue failure behavior is critically important. We can make complex next shift design, and that will benefit the aerospace industry, particularly the repair part. So our overall challenges which we are addressing within our center is looking at effect of these parameters: powder properties, process parameters, heat treatment, and machine. And all of these are affecting the real part properties or product properties, particularly defect generation, microstructure, surface roughness, residual stress, and anisotropy. So these are affected by these parameters in different ways. For example, heat treatment, which is a post-processing condition, will affect defects, anisotropy as well as microstructure. Machining will affect surface roughness. Powder properties will affect both defects and microstructure. And all of them, at the end of the day, this research is focused on cyclic properties. So you could see the interaction and interplay between complex parameters from the start, from the feedstock powder to the end, which is the post-processing treatment on AIM methods. Moving forward quickly, this I'm not describing in detail. We all know what is SLM, what is LDF, this community, we know that. But what I want to highlight is this part, ALSI 10mg alloy. It has got some nice properties: high ductility, high strength to weight ratio, high weldability, good corrosion resistance, good hardening properties, and much cheaper than our favorite titanium alloys, right? So this alloy, if we can get through the certification line, there is a clear benefit for aerospace industries. Okay, what we did, one of the fatigue properties of LPBF AISI alloy, which we know now. What we know is, as with other AM metals, compared to as built, we have much better properties for a machine. As you can see, for the existing literature show that. On top of machining, if we can apply stress relief, or what we call peak hardening, or HIP, or even platform heating. So we can change the post-processing or pre-processing. During processing condition, we can really achieve very high axial stress capability. So that means combined effect of peak hardening and machining can improve the fatigue strength significantly. So this is one of our key processing conditions we are going to deploy for the aluminum alloy. Now, Because of the complex factors I have shown, we had to first hierarchically identify what is the most important factor to the least important factor. And that's what we have done in this chart, again based on an extensive literature survey. So what we found, what affects the AM fatigue properties in AM, and this is based on SN curve is our first goal, but what we prefer looking at fracture mechanics. Because fatigue is controlled by cracks, and cracks are controlled by the mechanics of fracture. So we are trying to understand everything from the bottom level of fracture mechanics. Looking at controlling factors, surface roughness affects most, and then the porosity, then microstructure, then anisotropy, and then residual stress. Other people have observed that as well. Surface roughness, of course, because fatigue failure initiates as surface or subsurface defects. Machining can improve fatigue life. We can see high scatter in SN curve. Porosity control where the crack initiates, and again within the porosity, the location of the pore has more influence than the pore size and the pore volume. So location, subsurface or within the bulk will play a deeper role. In the microstructure, it enhances plaque nucleation and propagation, and obviously controlling the grain structure with the build direction, we can control crack resistance within the material. So that we have to understand, but that effect is less than porosity. And finally, of course, additive manufacturing, we have 0, 90, 45 build, that will introduce anisotropy. And finally, the residual stress. Now with that, what I want to highlight is this effect, what we already see in the literature. Depending on the build directions, we can get a change in delta KTH, which is the crack growth resistance in the material. So as you can see with this red font, if we heat treat both perpendicular crack propagating perpendicular to the build direction and parallel to the build direction, we can get very high delta KTH, which is fatigue crack growth resistance from AM material. So build direction has an important, whereas as build gives you really poor crack intensity threshold. However, if we apply a processing condition, stress relief or platform heating for stress relief, we can improve the crack growth resistance significantly, about 3.5 to 3 from 1.5. We can nearly double it. So this is our first protocol to increase the fatigue properties or fatigue crack growth resistance of this alloy. Now what's the key objectives, and I'll then straight away go to the results given the time issues. We wanted to, in this program, we wanted to investigate experimentally and numerically fatigue characteristics and properties of ALSI 10 mg alloy, which hasn't been studied extensively, and relate to, that's the key importance for aerospace, fail-safe and damage tolerance design. And what we want to do, we want to do that for SLM produced bulk aluminum alloy while operating within the service stroke range. To do that, we will be looking at, and the results I'll be presenting will mainly cover effect of stress loading, effect of surface, subsurface defects, effect of post-processing, effect of build orientation. So these are the 4 things we'll consider, and my results which will follow, which will show that. Now this talk, I'm going to talk about RO1 and RO2, which is the research objective 1 and 2, which is effect of size and type of defects and fatigue condition on fatigue strength and crack growth threshold properties, and we try to understand the effect of post-processing parameters on fatigue performance. There are 2 other goals, which are 3 and 4, doing detailed modeling study and developing predictive model, and finally using similitude methods. The similitude law RO4, there's a presentation today here. I'm presenting that tonight, so you can come and have a look what I'm going to say about objective 4. Okay, let's go through the methodology. I don't need to tell too much. We have done 4 different 5 minutes here. 4 different types of tests: axial fatigue, fatigue crack growth, fracture toughness, and low cycle fatigue. So it's a comprehensive investigation for this alloy to characterize every aspect of fatigue. This is the details of the presentation, powder composition, machining parameters. So if you're interested, I can send you the slide and you can look at it. So what we did for axial fatigue test, we first characterized the defect in the material. Go back. Yeah. We characterize the defects in the material, particularly 2D and 3D defects and surface roughness. After defect morphology characterization, we did high cycle fatigue test, different build directions, different R ratio, and different post-processing as-built machinery treated, and we did do post-processing using SEM and micro-CT scanning. These are the details of the different machines we have used, so if in case you want to repeat this kind of test. But then we are going to present these 4 effects. The effect of build orientation, it is very important. We found there is a high scatter and no significant effect of build orientation at a high stress condition. So you can see at high stress, these fatigue flags are same at a high stress amplitude with no effect of build orientation. At a lower stress level, lower stress amplitude, you get a large scatter. This is completely reverse cycle. Tension, compression, loading. Large scatter we observe at a lower stress. Build orientation, we believe in this case, may be suppressed by the scatter present in the data. That is our belief. To confirm that, these are the data which shows you the build orientation has relatively little effect on the fatigue. But to confirm that, we always go to the fundamental fracture mechanics, and we did a critical stress intensity factor calculation with using this formula. We calculated the critical length by the measurement from the SEM micrograph. And when we use this critical length and FW, the factor 0.65 for surface crack, we found the critical stress intensity is same for both horizontal, vertical, and 45 degree bend. So that explains fundamentally why we do not see the effect of build orientation. Then we move further to look at effect of post-processing parameters. And what we see here, again, a high scatter is observed for as-built and machine polish. Machine polish will reduce the roughness, and we can see very high scatter in the data. And finally, when we look at the results actually, as we see in the morning presentation, it is always recommended machined and polished substance will have a much higher fatigue life. As you can see, this table is almost 3 times the fatigue life compared to at all the stress levels. But always we have to important there is a high scatter involved in the data. Let's then look at why this happens. We wanted to understand why the scatter is present. We looked at carefully the type of defects we see in the aluminum alloy, and what we found here is this kind of gas pores, LOF, lack of fusion defects, and satellites, which are unmelted particles, and some of them can have a size of about 20 to 25 micron. So this as-built surface, which is not a rough surface, but it also contains these different types of defects, and that really causes the early failure. So it's a synergy we were talking in the morning between the surface roughness and the defects underneath it that causes this. Then we looked at the limitations of as-built sample, and as you can see here, as-built and as-built here at low stress, of course, low stress amplitude, you can get a high fatigue life, and if you get a higher stress amplitude, why is changing automatically? Yeah, what is important here to understand, if you look at machined, we get 3 times fatigue life than as-built for the same stress amplitude. This is because the multiple crack site initiations happens for the as-built sample, whereas a single site is found for the machine surface. So again, fracture mechanics shows it's a multiple initiation of cracks which causes the drop in fatigue life significantly for as-built sample. Moving further, the key conclusion tells us why machine surface is bad for the fatigue life. Then we looked at CT data, computer tomography data, and we found here very high porosity near the surface. 1 minute, okay. It's hard, okay. As-built, I've got 2.5% porosity near surface, whereas machined has got 1% porosity near surface. So that shows you, again, there's a relation between the porosity and the machining, and that causes the effect on the fatigue life. So basically, it's a reduction of porosity which is responsible. So this kind of summarizes what the effect of post-processing parameters have on fatigue of aluminum samples. Given the time remaining, I will quickly go to the surface roughness, which is a key effect, and what it shows you, there is no correlation between the surface roughness and the fatigue, as you see the scatter all over the diagram for all the stress level for vertically machined surface. And the reason of this is, again, the porosity of underlying the surface which dominates in this case. As you see, in this case, 2 samples, same porosity, different surface roughness, much rough surface, but fatigue life is 3 times than this. Although the roughness is higher here, 1.5 times higher, fatigue life is nearly 2 times. Why? Because the pore here is a smaller pore, and pore here is a larger pore, which controls the fatigue failure in this specific case, which we have been seeing. This, I will explain this probably and then conclude. What it shows you, the synergistic effect, we try to investigate in more details. Look at the thing clearly. If you have a same stress level, the pore size affects the fatigue life. Smaller the pore, higher the fatigue life, right? However, there's a difference between the surface pore, which are solid circle, and the internal pore, subsurface pore, which are open circles. If you have a subsurface pore that are less critical, that will allow you to get higher fatigue life, much higher, compared to a pore which is on the surface of the same size. So it is not the size only, also the location of the pore which is affecting the fatigue life for both horizontal and vertical built specimen, as this diagram clearly shows you. Okay? So this is the key thing of the synergistic effect. Finally, as you can see, pore shape is important, not only size and location. And you can see these pores are gas pores which are much more regular. This is lack of fusion pore which are tortuous, and that can reduce the fatigue life from 500,000 to 100,000, 400,000 to 120,000, just because it is a defect of different nature, every other conditions being same, right? So that kind of thing leads to us, we need to characterize this defect in very detail from fundamental physics point of view if we want to get fatigue life prediction right. Last point is the effect of stress loading ratio, which already we know well. We did tension, compression, tension, tension. There's a fundamental story here. Of course, you can see tension, tension gives a lower fatigue life than tension compression with a log linear curve with a Baskin equation. Now, why it happens, our ratio effect this is again we looked at the fundamental scale and looked at the CT scan data of this and showed that after tension compression test, which is R-1, the pores are closing. Some of the pores disappears due to crack closure effect, which gives you a higher fatigue life. But tension test, this is a cumulative frequency distribution. The pores are opening up, which are creating multiple crack initiation sites and affecting the degradation of fatigue life because of the R ratio. So this is the fundamental way we want to investigate this research. Again, looking at that, you can see what is happening from fracture mechanics point of view. When a crack initiates, the stable crack growth region is larger for tension compression loading than for tension tension, which drops the fatigue life significantly. So it's a stable crack growth region which causes the larger length of the stable crack growth region for completely reverse. Tension compression loading goes to increase in fatigue life. Finally, I think I don't have time, but I've done the last thing is heat treatment effect, which is also shows if you use heat treatment, you can significantly get an increased fatigue life compared to as built and machine. You can see 500 hours of heat treatment gives you a 10 times more fatigue life, and because what happens during heat treatment again, grain boundary disappears and filled with SI particles in this case. So grain boundaries promote crack nucleation. We remove them, we fill it with foreign particles, okay, because of the heat treatment, and that raises the fatigue life. Again, it links to the fundamental microstructure and chemistry. Okay, with that, I'd like to conclude my presentation, but remember, whole key thing is we did some tests, we looked at the results, made conclusions, then going down to the fundamental physics or metallography or microstructure effect to understand that. For example, heat treatment, you can see if you have no heat treatment, you get these dimples with cleavage face, which will cause you a brittle fracture, lower fatigue life. If you have heat treatment, you have larger dimples, round shape, which will cause you ductile fracture. That again will explain you why you see a different effect. That's my summary. I don't think I have time to go through, but you can read the summary. The key conclusion is we have performed a detailed characterization of fatigue response of aluminum alloy with the view of we'll be able to meet the fail-safe and damage tolerance criteria for aerospace application. Thank you very much. But if you have any comment, you can talk to me anytime. I'll be back for the next presentation.
Yeah, so I also want to say that we will start the next